Hello again. In the last lecture we showed you how to start the analysis of a system design problem. In this lecture we'll look at the three identified problems and how to solve them. First problem is the input range of the ADC is between 0 and plus 3.3 volts. That's defined by the power supplies of the embed. However, audio signals are usually centered around 0 volts because you get positive peaks and you get negative peaks. So we need to modify our circuit to deal with this, i.e. we need to be able to accept an input centered around 0 volts into the embed. The output range of the DAC similarly is between 0 and plus 3.3 volts. And we need an output, a signal centered around 0 volts. If we didn't do that and we amplified a DC signal at say plus 2 volts, that would pass a large DC current through the loudspeaker and it would eventually burn out. It would fail. So we need the signal driving the loudspeaker to have positive peaks and negative peaks centered around 0. So these are the limitations that we're seeing from the embed itself, and the input signal can go down as far as 0 and up as high as plus 3.3 volts, and on the output side it can go from 0 volts up to 3.3 volts. Let's try and solve these problems. Let's look at how we can address these to make the system work the way we want it to do. So, repeating the three problems we've just had before. First of all, we look at the datasheet for the ADC. It's part of the embed datasheet. The embed datasheet is about 200 pages long, and I had to search through it to find out what the input impedance and load of the ADC was from the embed. And we found it there in the datasheet. And the datasheet says that the load is 50 k ohms. Good. So, what we could do is we place a 1-to-1 potential divider using two perhaps 10 k ohm resistors, which will apply a mid voltage to the ADC input. Now you say, why would you do that? Well, remember that we're trying to input positive going signals and negative going signals. So we have to have equal headroom from the center point going up as from the center point going down. And ignoring the small load that the ADC input impedance will have, the middle level here is approximately plus 1.65 volts because it's 2 10 k resistors, which divides 3.3 volts by 2. We've also included a capacitor here, and that capacitor allows us to connect or remove the DC component and allow us to connect a signal that is symmetrical around 0. It's important to realize that you need to calculate out the value of that capacitor because that will reject some of the low frequency information, so you need to make sure it passes all the audio information. And I have chosen 1.6 microfarads into a parallel impedance of 5 k ohms, that is 10 k ohms in parallel with 10 k ohms, and I am still ignoring the 50 k ohm input, but strictly I should have considered it. And that gives us a pole of 20 hertz of 1.6 microfarads going into 5 k ohms. So we now are able to take an input range into the ADC that is centered around 0. Let's look at what we can do in the output stage. Well, actually we can do pretty much the same thing. We've got I've used a 1.6 microfarad capacitor to couple to the ADC output, and I've also used a 10 k ohm load to 0 volts. That again forms a pole slightly differently, about 10 hertz this time because it's 10 k ohms instead of. But that will allow you to pass the audio information from the ADC and from the DAC outwards. Of course, it means that the DAC at 0 signal must be biased at mid-rail at about plus 1.65 volts as an output voltage. So it has 1.65 to go up to plus 3.3 volts, and it's got 1.65 to go down to 0 volts. So now we've produced a signal that is symmetrical around the 0 volt rail. So at the input stage, we can now couple our zero-centered input signal, and at the output, we can now couple it onto our power amplifier. So let's plug the other blocks onto the system around this. Okay, we've got our microphone, which produces a typical signal of about 1.6 millivolts RMS. That's me talking reasonably loudly, but in sufficient headroom. We have an input amplifier. We still don't know what the gain of this amplifier is, but we can now calculate it because we know what signal we want at the output of the amplifier. We know what signal we want at the input of the amplifier. So simply the input amplifier gain is 1.6 volts peak divided by 2.6 millivolts peak, which gives us a times 730 gain, or 57.2 dB. It would generate a signal that swung between plus 3.3 volts and 0 volts, with a centre point around 1.65 volts. Similarly, for the output, we need an output voltage of plus and minus 9 volts peak to generate our 10 watts RMS into the 4 ohm loudspeaker. Using the same equations, we know what the input is this time, and we know what the output is. The output is 9 volts peak. The peak input signal is 1.65 volts peak. So for the output amplifier, for the power amplifier, we need a gain of times 5.45 or 14.7 dB. We can select our display, whether it's a bar graph or an analog version. I've chosen the bar graph here because it will be easier to drive from the embed digital functions. And finally, we look at our power supplies. So we now have a system that has been designed from end to end to deal with signal levels. Now we need to look at the power supplies. So the input amplifier needs a plus and a minus signal to produce plus and minus 1.65 volts peak output. For this amplifier, we have a relatively free choice as long as it's greater than 1.65 volts. We know that the embed is being powered by plus 3.3 volts, so why not choose minus 3.3 volts as the power supply for the input amplifier. The embed is constrained for a maximum voltage of 3.6, and the working voltage will be 3.3 volts, which is safe. We know the output amplifier will need to produce plus or minus 9 volts peak to produce 4 watts. And I have assumed here that the output amplifier requires an extra 1 volt between its maximum output level and its power supply to operate. So we now have power supply for the input amplifier of plus and minus 3.3 volts. We have a power supply for the output amplifier of plus or minus 10 volts. So we have now completed our design. Now we've designed the system and we go back to the customer. And then he poses some questions. How large a battery would be required to last all the way through a 1-2 hour lecture? We can work out how much power the circuit consumes by adding up the current consumption by the input amplifier, by the embed circuit, and also by the output amplifier. But then the customer says, okay, I now want to sell this to rock musicians. How long would the battery last now? We can calculate it out, and we can calculate out how much and how large a battery would be. If the output power is 6 volts RMS into 4 ohms, which is 10 watts RMS, then do we require a heatsink on the iPhone? And if so, how large? But you can see how quite a reasonable request from the customer requires you to go and do further analysis on your system to answer that question. I finished up with a rather strange question. Am I allowed to take this equipment on a commercial airline flight? Now all of you may be saying, well, of course you can. But actually there is limits to the size of batteries that you're allowed to carry on a commercial airline flight. So these applications and design questions, they do not sound technical. There's no mention of volts and amps and ohms, but you, as the system designer, need to perform a full engineering analysis to get the right answer. So I've come up with 6 rules for system designers. Rule 1. Find out what the customer is trying to do, not what they say they want to do. You're the system design expert, not them. Talk to the customer and agree a set of requirements of what you will do to meet their need. Think about the whole problem and identify the major tasks, functions, blocks you need to perform that task. Don't just think about the amplifiers, think about the entire problem. The 4th rule is look at the interfaces. What is happening between the blocks? And that's where you can make a difference. Number 5 is look at the physical limitations. The power levels, the signal levels, the heat. How do you deal with it? And the final one is think about validation and verification. Validate with a customer what you intend to do and verify by agreeing a specification with the customer how you will prove you have met the requirements. I hope you found this interesting, this walkthrough of a system design. As I say, it was a very simple system design, but it captured a lot of the elements that you can apply for any system design. Thank you very much for your attention, and I look forward to any questions you have. Please contact me and I'll try to answer them. Goodbye.